Hey everybody, and welcome back to Physics, Chapter 4. Today we're going to talk about, we're going to talk about this right here. Two-dimensional, that is, we're going to talk, so far we've talked about motion in the x direction, you know, all of our car examples. And we've talked about motion in the y direction, you know, like all of our balls dropping and throwing balls up kind of question. We've talked about x, and we talked about the horizontal direction and the vertical direction. Now, so far we've called them both x, if you've noticed. We really haven't called the vertical y. But we need to distinguish them now, because now we're living in a land of two dimensions. And so we're going to call one x, and we're going to call the other y. And we're going to talk about motion in two dimensions, not just along a straight horizontal line or along a straight vertical line, but along a line, in this example here, that is not on either axis. Okay? And we're leading up to something called projectile motion, which is just about nearly as fun as it sounds. So, two-dimensional kinematics, that's the name of the chapter. Two-dimensional kinematics. Now, kinematics is just a word that means when you talk about motion without regard to what is making something move, forces, that's called kinematics. We haven't talked about forces yet. That's coming up in the next chapter, chapter 5. And believe me, you'll know it when we get there. Kinematics is just a description of motion without really talking about forces. Sometimes those three equations that we've called the equations of motion, for constant acceleration, you know the ones, v equals v naught plus at, etc. Those are sometimes called kinematics equations. So we've been doing kinematics all along. Not really talked about forces, not really. We talked about my hand pushing a ball up, or maybe gravity, but we haven't really considered gravity as a force. Anyway, two-dimensional motion. And the first case here that we're doing in this particular video is the case of constant velocity. And of course, velocity is speed and direction. You remember this because you're alert. It's a vector. And so right here we have an example of constant velocity, two-dimensional motion. Two-dimensional kinematics. It's a turtle. Okay, very dramatic way to start things off, you know, with a bang. A turtle moving from the origin up to some point up here. This particular turtle has constant velocity, 0.26 meters per second at an angle of 25 degrees above the positive x-axis. We'll get to this drawing, and we're basically going to consider answering a certain question in two different ways. And the question is this: how far has the turtle moved in the x and y directions after 5.0 seconds? So we're looking for an x length and a y length. How far has the turtle moved in x and y directions, right? Because the turtle is not moving just in x, and the turtle is not moving just in y. The turtle is moving in both directions. So what you see here is this pink dotted line here tells you how far the turtle has moved in the x direction. So he stops right here, okay, at the end of the arrow. This is his displacement vector, okay, the pink one. He's going to start here, and after 5 seconds he's going to be there. We want to know what the value of x is here, what the value of y is there. And of course this is a right angle. If it's not a right angle, it's a wrong angle. So there's a right angle right there. And we want to know what the values of x and y are after 5 seconds. How far has he traveled in x? How far has he traveled in y? That's the question. Well, it's not hard to answer. Okay. We know the hypotenuse of this triangle is d. It's the total, it's the magnitude of the displacement, d. Now we call displacement delta x sometimes we call it r. Displacement has several different things we can label it, but in this case we're labeling it d. So what is d equal to? That is, how far does the turtle move off the origin? Well, that's not hard to do. D is v naught times t. That's by the very definition of velocity, right? Actually, v and v naught are the same thing, right? Because if it's constant velocity, then v equals v naught all the time. It's only got one value, and that's 0.26 meters per second at 25 degrees. Okay, so d is v naught times t, right? This is distance equals rate times time. Okay. And so we know what v naught and t are. So this is equal to, we can find out what d is equal to. D is equal to v naught, which is 0.26. Time is 5.0, and that's going to be in meters. So 0.26 times 5.0 is 1.3 meters. That's how far, that's the length of this line here. 1.3 meters. That's how far from the origin to the end point right there. That length, that distance there is 1.3 meters. Okay. That's one thing we need to know. In order to find x and y, right, we need to know d. And now that we know d and we also know the angle, we can use trigonometry, right, to determine the sides. We know the angle, we know the magnitude of the vector, now we can find x and y. Remember that x is the adjacent here, right? This side here is the adjacent side to theta. Adjacent is cosine, so x is just d cosine of theta. The y side here is the opposite side to theta, right? Theta's here, y is the opposite side, so y is d, hypotenuse, times sine of theta. So now that we know what d is, 1.3, we can find x and y and answer our question. Okay, so x, as advertised, is, actually what I'll do is I'll do it here. X is d cosine theta, which is 1.3 meters times cosine of 25. You do your math, you stick it in your old calculator there, and you'll get 1.2 meters. It's a little bit off that. I've rounded to two significant figures, but that's the answer. So x, 1.2 meters. Okay. First we had to find d, the hypotenuse, and then we used trigonometry to find this side of the triangle right there. So that's how far turtle went in the x direction. Didn't go the whole way in x. If he was walking all the way along the x direction, he would have moved 1.3 meters in the x direction and none in the y. If he was walking in the y direction, he would have walked 1.3 meters in the y direction and none in the x, but he was walking at an angle to both. So part of his motion was in the x direction and part was in the y. Y is d sine of theta, which is 1.3 meters, times sine of 25, which is a pretty small number. When you do this, you get 0.55 meters. Okay. So our question, how far has the turtle moved in the x direction? 1.2 meters after 5 seconds. How far has the turtle moved in the y direction? 0.55 meters. In the y direction. And 1.2 meters in the x direction. Okay. Now there's another way of doing this. So this is all all this here refers to drawing 1. That 1 and that 1 go together. Now I'll change the color of this 2 here, and we'll do some work in green. The second one, there's another way to think about this. Stay with me here. Don't drop out. Remain alert. Okay? There's another way of thinking about this. We can think, instead of thinking about a displacement vector and using this triangle here, we can think about the turtle's velocity vector. And we can draw that vector right here. I will draw it in orange. The turtle has a velocity vector right here. And it doesn't really matter how long we draw it. As long as it's in the right direction, we can say this is the velocity vector. It is also, right, because he's moving along that line. How does that show up? That shows up okay, I guess. That orangish, yellowish kind of velocity vector there. So it's also at an angle of 25 degrees. And we know that it has a magnitude of 0.6 meters per second. Okay. Now this velocity vector, like any vector, has components. It's got a component here in the x direction, which we call v naught x. And it's got a component here in the y direction, which we call v naught y. Again, the length that we draw this vector is not too important. Okay? The units of this vector are meters per second. It's a velocity. Okay? But you can see that we can think about this velocity vector as having an x part v naught x and a y part v naught y. And notice that what we have here, it's smaller, is another smaller right triangle similar to this one. They are similar triangles. Okay? But this is a triangle made of velocity vectors, and this is a triangle made of displacement vectors. But you can think in either way about it. Okay? So in this case, what we want to do is find out what v naught x and v naught y are. V naught x, in the same way that x was equal to d cosine theta, v naught x is v naught times cosine of theta. And v naught x tells you how fast the turtle is moving in the x direction. Okay. How fast he's moving in the x direction. How many meters per second is he creeping along this axis? Now he's not creeping along that axis. He's going along this line here. Okay. But at any given point, he has an x-coordinate. And that x-coordinate is changing as he moves to the right. The question is, how fast is his x-coordinate changing? That's what this number tells you, how quickly his x-coordinate is changing. Put in the numbers that you know. V naught is 0.26 meters per second times cosine of 25. And you'll get 0.24 meters per second. Okay, so v naught x is 0.24 meters per second. That's how fast the turtle's x-coordinate is changing as he moves up that diagonal line. Do the same thing with y. And this video may go a minute or two over. I do my best to keep them at 15, but this might go 16 or 17. So I'll do my best here without rushing. I don't want to rush. V naught y is v naught sine of theta, which is 0.26 meters per second times sine of 25. When you do those maths, you get 0.11 meters per second. So the turtle's x-coordinate is increasing at 0.24 meters per second. The turtle's y-coordinate is increasing at 0.11 meters per second. V naught y is, actually I won't. Yeah, orange is right. Equals 0.11 per second. That's really small, I know, but it's there. Okay. So now we know how fast the turtle is moving in both directions. What y-coordinate increasing 0.11 meters per second, x-coordinate increasing 0.24 meters per second. And now what we can do is to find out how far the turtle goes in each direction. Now we can write x is v naught x times t. Right? Again, distance is rate times time. The very definition of rate, the very definition of velocity, the very definition of speed, if you will. And so v naught x is 0.24 meters per second times time, which is 5.0 seconds. When you do that, you get the same thing you get here, which is 1.2 meters. Y is v naught y times t, which is 0.11 meters per second times 5.0 seconds, and that is 0.55 meters. So these answers here are the same as those answers there. This is doing the same problem in a slightly different way. This is looking at picture number 2 over here. I'm sorry, it should be green. But I try to color coordinate people. I really do. I love colors. Love them, love them, love them. I try to color coordinate. Doesn't always work the way I want it to. So this is picture 2. And the point of this, and I can't really see there, I see you now. The point of this, the reason I'm doing it 2 different ways, is to remind you that both displacement and velocity are vectors. In this first case, we used all displacement vectors. In the second case, we did the same problem, but did it in terms of velocity vectors. And the velocity points in the same direction as the velocity vector points, in this case, in the same direction as the displacement, because it's constant velocity. Okay. So there you go. We're at 17.5 minutes. I'm going to close it out, and we're going to pick up and do an example using this, okay?